Today's lesson is going to deal with what's called the efficacy of scientific notation. Now, it sounds quite fancy, but it is actually pretty straightforward. As you may recall, scientific notation is a way to write very large or very small numbers. What the efficacy of scientific notation means is, if you look at the word efficacy, it's a derivation of the word efficient. And what it's telling us is that scientific notation is an efficient way to write numbers when they are very large or very small, and when we want to perform math operations on those numbers. So, let's look at a couple of examples. The mass of a proton is some very small number in kilograms. Okay? What is that mass written in scientific notation? Now, it's clear that it's not very efficient to write the number with all of those zeros. But we know that we can convert that, as previously learned, into scientific notation by moving the decimal to the right. In how many places? 27. But it's a negative exponent because we're dealing with a very small number. This is a more efficient use of a way of writing that number than with the multitude of zeros that we see there. Now, similarly, we have the mass of an electron being a very small number. We'd like to convert that into scientific notation. When we do so, we get the number 9.10938.291 times 10 to the negative 31st power. Remember, the decimal portions of our numbers in scientific notation have to be greater than or equal to 1 and less than 10. Okay? Now, why did we do all of this? Well, let's say, as we are in example number 3, we're asked to compare these two numbers in a ratio form. You should recall that in math, a ratio is another way of saying division, and it can be written 3 different ways: using the fraction bar, the colon, or the word to. Well, we're going to use the fraction bar because we eventually want to be able to divide what we're coming up with here. So, we're comparing the mass of a proton, so that's our first number, 1.672622 times 10 to the negative 27th, to the mass of an electron, which is the 9.10938.291 times 10 to the negative 31st. Now, it wouldn't be of use to us to try to, or very helpful if we're going to try to divide these very small numbers that have a lot of decimals. They're not very small numbers, but relatively small numbers with a lot of decimals, or the decimal part. So what we're going to do here is round. And so instead of 1.672622, we're going to just round it to 1.7 times 10 to the negative 27th and 9.1 times 10 to the negative 31st. You should also be able to tell me which of these two is heavier. And which one? The mass of a proton, because negative 27 is greater than negative 31. Now I'm going to do my division of 1.7 and 2 and 9.1 to get approximately, I'm just going to move over here to make it some room, 0.2. When we divide with the same base, we subtract the exponents. Be careful with the signs. It's negative 27 minus, because of subtraction, a negative 31. Using our keep, change concept, we know that's a 4. Converting that to proper scientific notation is 2.0 times 10 to the third. We made this number larger. We have to make the exponent smaller, 1 decimal place, 1 unit down, which we can then convert into standard form of 2,000. So the ratio of the mass of a proton to the mass of an electron is 2,000 to 1. Where did I get the 1 from? Well, once I complete my division, okay, all I'm left with is 1. Let's take the next example. As of March 23rd of this year, the national debt in the U.S. was $16,755,133,009,522. And there is approximately 313,914,040 U.S. citizens. What is each citizen's share of the national debt? Now, again, obviously, if we have a calculator, we could take our calculator out and do these, but let's get fluent in using scientific notation. Let's round, okay? Now, there's different ways we can round these numbers and what we're going to round them to, but for the element of this exercise, argument of this exercise, we're going to round this to 17 billion, okay? And how do I write that in scientific notation? That's going to be 1.7. Let me make it a little nicer. 1.7 times 10 to the 13th power. How did I get 13? 3, 6, 9, 12, and I have to move over one more place to get 13. And then instead of 313 million, I'm going to say 300 million. It'll give us a close enough approximation. So how do I write that in scientific notation? 3 times 10 to the 8th power. 3, 6, 2 decimal place moves. Now, I'm going to do my division of 1.7 times 10 to the 13th over 3.0 times 10 to the 8th. I'm going to round that. When you do that division, it's 0.56. The bar over the 6 tells me the 6 is repeating. Subtract my exponents. Instead of 0.56, I'm going to round it to 0.57. Again, sorry, one step ahead. 5. Again, that's not proper scientific notation, so it should be 5.7 times 10 to the 4th. I made this number bigger by 1 decimal. I make the exponent smaller. Now to convert this into what we can relate to, times 10 to the 4th means to move 4 decimal places. I move once to get to the 7, add 3 zeros. So what is this telling us? That it would cost approximately $57,000 per person to pay off the national debt. Quite an astounding amount of money when you think about it. And hopefully they won't be coming to knock on your door to ask for that money. So, again, today's lesson did not teach you anything new with regard to scientific notation. We've gone through all the lessons for adding, subtracting, multiplying, dividing, from converting to and from scientific notation in standard form. All that we're now doing is we're taking actual factual situations and using scientific notation because it's something more efficient for us to utilize.